Thank you. Thanks for inviting me. I had not missed a conference in honor of Tim. So, and I was with Jan Werner, who's a colleague of Tim. And yesterday, some of you were in the talk of Bob Lucas, and Albert said that this was the Bible. I suppose it meant the Bible of economic dynamics, okay?
Some people said.
And that reminded me that, we have quite a few things in common in Tim. One is that we are both young economists. So, and another, we spend a lot of time in different ways, in different forms and times, but here at the Autonoma. Also, we were colleagues in Minnesota together, and presidents of SED and other things. And we had a few beers together too. But there is something we also had in common, is that we were raised Catholic, okay? So we had images like that in our childhood. And that made me think about, the Divine Trinity. And that's an alternative title of the paper that my colleague doesn't know. It's called The Divine Trinity of Dynamic Programming. So it's a follow-up of Lucas Stocky. Okay? And so here it is, the deal. So we go back to standard Lucas dynamic programming. So all the things that you guys teach in the first year, okay? So let's go back for a few minutes to what we do all the time. So as a standard problem, okay, infinite horizon with constraints, and then we make standard assumptions of convexity and interiority, blah, blah, blah. So everything is a standard. And then we can also, we don't do it a lot, but if we want to think that these things, constraints might be binding, yeah, Stocky Lucas, they'll have always interior solutions. We'll come back to that. So we can just write down as a saddle point problem, okay? And now we can just write down the Euler equation, and it will look like that, okay? So now the multipliers, and so that's the Euler equation of this saddle point. Usually we have interior conditions, so we just go to the thing we do all the time, the Euler equation that we see. And we can also know that this is a second order difference equation. And then we just have the standard sufficiency theorem. So on the standard assumptions we made, and a transversality condition, because it's a second order difference equation you need as a terminal condition too, this thing is a solution to the original problem. So there's the sufficiency theorem. So what we get from Euler. Then we go to Bellman, and we do all the time too. So then we just have a value function for the same type of problem. And then if it's concave, we can just, we'll go on. And we can also write down the Bellman, saddle point Bellman equation. Usually we don't do that, but we could do that, okay? If we are thinking about the constraints. And we write down the first order conditions. Okay, and of course that's the derivative of the value function with respect to the choice that we're making now, y. And here is where the envelope comes. Okay, and we say, well, we know what's the derivative at x is like this, then we just plot them all together and we got the Euler equation. So we had gone from the Bellman to the Euler equation. Okay, that's fine. And then we're going to have policy functions. And actually, we plug in the policy functions. On the Stocky Lucas book, they do too. Then, oh, that looks like a first order difference equation system. Okay? So that's it. Okay? So we have, in Euler equations, it's good because we have the necessity and sufficiency. But then it's very convenient to have the Bellman equation because we have the value, the policy, time consistency, and we go from a second order to first order, but then we use the envelope to link everything. So everything ties together. That's it. Okay? Now we look at and we just say, okay, what about without differentiability? Because I use differentiability there, no? As a matter of fact, when I did this, is because if I know the value and it's differential, I also know the derivative. I know both things at the same time. Okay, so, but now we had to stop back because we didn't find a proper envelope to do that. Okay, so the main, I think the paper has two contributions. One is just to get down the envelope the way that we would like to have it. Okay, so just we go back to a static case because that's where we can do it. So that's a standard problem, maximization. That's even before we do dynamic programming. And again, we make a standard convexity assumptions, an interiority condition, and we might or might not use concavity. Okay? And we just write down the Lagrangian. And again, we look at the saddle points. Okay? And if we have this Lagrange condition, we're just going to have that this is the value we got. Now, one has to be careful with this, okay? Because when we look at the saddle point solutions, they're the ones who have more structure. And in particular, it's like we have these two sets, okay? It's the product of these two sets, which corresponds to the solutions, to the saddle point solutions to this. Okay? So there is a theorem of Milgram and Segal, and then we extend that theorem. It says, okay, if a function satisfies these properties and also these partial derivatives are continuous, blah, 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 the left hand and the right hand side derivatives are well defined. Okay? So you know that you arrive someplace. We also know that the concave function is almost surely differentiable. Okay? So that typically we will know everything. But then we just work on that a little more. And then, for example, if we know so many conditions to get the value function to be differentiable, one is, for example, that there is a unique saddle point. Okay? And if it's differentiable, then we get what we were using before, the gradient. Okay? So if it's concave, then we have the superdifferential, which is all the vectors that satisfy this. Okay? And that's exactly what we just support with the superdifferentials. So that's the main theorem on the envelope. So you crank this thing out, and it turns out that this takes this form. So it's like looking over the solutions, multipliers, and the multipliers and the solutions, so the union of that, and then intersect all this, that stuff is the superdifferential. So the first looks strange, but then when you work with it, it's sort of fairly easy to work. Again, now the value function is differentiable if the saddle point multiplier is unique. Now this is one line proof of the famous Benveniste-Shakman result. I don't need to do anything, just that. Why? Because they look at the interior solutions. The multiplier is 0. That's it. Proof. Okay? So that's really good to check differentiability. And we also have other conditions, but I don't bother you. So now I'm just going to go through the same exercise, okay, that I was doing before, but now without assuming differentiability of the value function. Okay? So we go back to the saddle point Bellman equation corresponding to the value function. And again, this is the product of this set, which is the one that show up here. Okay? And now the first order condition simply says, so now we do subdifferential calculus, okay, that there is a subgradient vector in a subdifferential that we have the zeros, it gets a 0. Now, we apply our envelope, and this will say at x, that will take that form. Okay, so because we have one of those. Okay, so we'll have this form. Will we associate to this subgradient, there will be a multiplier. Okay, so this will be the relationship. Good. Now there's a problem. So that slide is a key slide. Okay, so once we understand this, basically. So what happens here? Now if I look at the first order condition, now I started an xt minus 1 to have now the function is not going to be differentiable at xt. Yeah? So this is the first order condition that I just told you. The subgradient that this gets 0. But this means is I'm making a selection, okay, out of this set, the superdifferential. So therefore, as I told you before, corresponding to this subgradient, there is a multiplier. Okay, so when I do the first order conditions, here I'm making a selection. Of course, if it was differentiable, there is not much to select. There is something. That's it. I know it. But now, okay, I do something that before I was doing mechanically, I had to be more careful. Well, if it's not differentiable, and I apply the envelope next period when we start xt. Because I was sitting down xt minus 1, deciding the choice on xt. Now, next period, I make a selection. Well, how do I know that it's the same? It might not be. And if it's not, then there is no, and I just plug this thing, that's not going to be equal to 0. The Euler equation is not necessary. So we don't have divine trinity anymore. This is the standard problems in the night programming. So, okay, so say, yes?
The Euler equation of the value function formulation.
Okay, what yes.
The Euler equation of the...
Oh, the infinite? No, I told you everything. That's exactly. Euler was right here. Okay, Euler is right. What does this mean? Okay, but because the one nice thing of value, what I use in night programming is that I know the state, and I start the program, the Bellman equation. Now, here, what this problem is you told me the state is xt star. That's it. Well, then I have to move from here, do my solve point for that. I will get this. I don't know what you did last time. As simple as that. Of course, that also gives you immediately the intuition of what you will need to solve the problem. Okay? But another thing to this in the standard dynamic programming continues to be. Well, I said it's not necessary because this is as optimal as it was before. Okay, so if I do a standard dynamic programming, this. So what happened? Here's like the multipliers are inconsistent. It's like a weak form of time inconsistency of the multipliers. Okay, so like because I hit a king, and there are many prices. And once I'm hitting the king, think of some price, and then when I start, I use a different price. But it's the same point, so who cares? Okay, so I was telling Nancy, so who cares? Yes, you should not care much at this point. And probably that people didn't even pay attention to that. Okay, so, but here I tell you, so immediately we get the solution to that problem. So we're going to impose a consistency condition on how we do the selections. Okay? So we'll impose an envelope selection. This says, well, this stuff has to be satisfied. And exactly Euler was right, because when I was doing the whole infinite horizon Euler equation systems, that was being satisfied, because I was keeping track of the second order difference equation. Okay? So that's why it's a corollary of the standard sufficiency theorem. But this says, too, that now, if I do dynamic programming, I should know that. So we do the selective value function. What is the selective value function? The selective value function is just take any function which is concave, or whatever, it could be convex, whatever. So when I put the stuff here, says, when I do the envelope, our envelope, because it's a set, even I write this thing, I mean I'm using that selection. So it's, of course, in the differentiable case, there is not much to say, because in the differentiable, there's only one thing. But in the others, not. So that's the necessary and sufficient amount of information that you need. That's it. And with, I mean, this, of course, comes out to the work we were doing with Albert, and we discuss a lot of these kind of things. And we put a condition, which is in our, that will imply the condition we have, Albert. Okay, so if you do that, okay, So you're saying that now, when you choose this multiplier, has to be consistent with the selection I made. Okay? And of course, then this also gives me a transition to next, so I can write down like a Bellman equation. Okay? So this is for the standard case. Okay? So that's it. So now we recover all the stuff. Okay, so we recover what we had done before. So that's it. So you encounter a problem of non-differentiability, which is, you might happen, we have nowadays a lot of problems with binding constraints, many more than when they wrote the Stokely-Lucas. Okay, and so those things show up. Well, that's what to do. Okay. So, okay, we got that. But now we go to the stuff we do with Albert, recursive contracts. Okay? I will finish soon, so that's good. So that's a standard canonical problem. Okay, a partnership problem with a bunch of guys. They have some income process. I can put capital, but who cares now? So, and it will have a law of motion. And then we put limited participation constraints, like limited enforcement, in every period and state. Okay? So we know all that stuff, that when you put these constraints, okay, with forward-looking constraints, we call them, the standard dynamic programming breaks down, but that's why we did all that stuff, so this, we know how to do that. And we make standard assumptions. Again, that's nothing, and just this is, we make this because then it's trivially to extend it to the stochastic Markov process. Blah. So here is the stuff with Albert. Write down the recursive contract problem, where now we have these mu's, which are the aggregation of past multipliers. Okay? So now we're going to have this saddle point, but now it's because we have these mu's, okay, that, and now we look at the here, we have an infinite horizon problem, all right? So we have done what is called able summation here. And if this is the Lagrange multiplier of the mu's, okay, these co-states, the first order condition looks exactly like this. Okay? And we can just look at the universality condition. So now we are doing Euler again, except with recursive contracts. All right? Now we can write down our saddle point Bellman equation here. Okay? And again, this now will be the product of, so, okay, I didn't write the whole thing. There is a saddle point of the saddle point, which includes the mu and the gammas for this constraint, okay, and so on. But anyway, we have the whole thing here. Okay? So this is a particular case. This is a particular case that, as you see here, when we look at the, oh, here it is. When I look at the superdifferential, actually the subdifferential, because now it's coming back to the other side, this is the value, outside values, plus a set of the multipliers of the constraints. That's a nice characterization. Okay, it says, or either, so when this is 0, you just, is when it's binding. Okay, when it's binding, that's 0. Okay, so, and the mu's grow up. But if not, you might have be above, but how much? Well, exactly by the multiplier on these mu's. So it's like getting inside of our recursive contract, see what happened there. So again, now we do the same thing as before. Okay, so we're going to be the first order condition, thus we're going to have a new subgradient here. And also, what I said, since it's homogeneous of degree 1, this had this structure, which in the paper with Albert, we exploited much more. Here I just mentioned it. So this means that it's like the sum of these subgradients, which exactly takes this form. Okay, so basically all information is in these lambdas, and then on the weights. Okay? And so that's actually what it says, because if I change, so notice here the difference between the previous case, the standard dynamic. Now if I change the selections, I'm changing values here. That's going to have an effect. Before I was only maybe made a mistake with the prices, but I was not changing the allocations. Here values are promises of allocations. So I have to be more careful. Okay? But again, the same thing as before. If I impose the envelope selection condition, this thing is there. Okay? In the paper with Albert, the last sufficiency theorem, it has a condition which is basically imposing the Euler equation. So this implies what we have, basically. Okay? So now we just go. Of course, and then you say, well, so now let's do the selective value function too. Here. So the selective value function, I'll put the subgradient here. Except there is a little funny thing here, because now this is uniquely defined. So if I say, I can say, to be consistent with my notation, I say, like, you're maximizing respect to the line. There is nothing to maximize. It's just one number now, because it's the separable case. Okay? But that's fine. That says you do this, you do that, and then you do as before. Okay? You're going to choose something there, and that will give you the law of motion. Okay? So with the selective, so basically that's what we generalize the stuff we did with Albert. So now you have the state variable, the mu's, which are the co-state variable that we had before that tells you when this thing is binding, and the new stuff, which can you think just be the lambda if you wish, which tells you how these mu's were changing. And that's it. Okay? So now we go back for a second and look at this example, which is where the headache started. Okay, which is one done here in Autonomous when those guys were working hard on that. So they did this example, and so I said, what's going on the first time? And they said, oh yeah, of course, this is non-differential, so we should use differential. But I had this idea, but no clue how to do that stuff. So we discussed a lot with them, but we didn't go anywhere much. So until then, I realized how to go along. So this is the example. So the difference here is, of course, is linear. Okay. So linear means that of course, that the Pareto frontier might have flats. Okay. And in these flats, the planar might be indifferent between the allocation across those guys. Okay. And we have the constraints. So now I just put it in this framework, okay? So again, so we use the Marimón cell value function, here it is. And it has this structure, okay? So it means, of course, if you put more weight in one agent, you give everything to that agent, because you are this neutral, okay? So it's only when you are indifferent, when the mu's are equal, but then it's not differentiable. And here is the set. Graphically, I changed the phi for omegas because that's what we're used with Albert. So that's exactly how this looks like. Okay? So if I plug the value function as a difference of the values, it has a kink. And if I look at individuals, they will look like that. Jump. And if I look at that set, that will be this. I can also look at here The same thing, so this says, well, if I have choosing one here is like choosing a lambda. Typically, I might start here. Okay? But I might have many solutions. The only thing is that I had to be consistent. Okay? Because if I choose here, but then next period around, since I'm indifferent, the planar start here, the planar is indifferent, but the guy are not. Okay? And therefore, what was before a weak form of time inconsistency of the multipliers now might result in an inefficiency. Okay? So if we solve, these are just count equations. So when we look at we just did it before, no? So here is how they look the first order conditions. Okay? And it will look like this for consumptions. So this will determine here, so of course it will have, so we have these many solutions that all these things can bring. So when you pick one, you will just have to, so you have this, and then that, and the further conditions, blah, blah. Those are the equations that those guys were working. But what we do here is we add these two, which are the consistency conditions that we set, and the fact that these things have to add to the whole. Okay? So that simplifies what we had before. And then many things will happen. One is like, so you can have still many paths, but all the paths will satisfy the constraints. Okay? And so on. So what happens exactly this? So they were only looking at this. And then you can have all kinds of solutions, which correspond exactly to what I was telling you before, is that you make a choice, like you decide the consumption on period. So for example, you start in period 0. No? In period 0 almost surely will be differentiable. And in this case, as long as, for example, you start that in the problem, you give less weight to the second. So this problem is putting weight 1 to the and weight 0 to the other. Okay, so that's differentiable. So you are in this case, fine. So you just put 1 at the bottom. But then the second period you will hit immediately. You put the both at the 1. So in the second period you just here, someplace. Okay, typically you will be here. Okay. Now you have free between what is the consumption in period 0 and the promise, if you want, from the future on. Okay? So many things you can choose. You can choose even give 0 consumption in period 0 in the future and so on. So you have to think, there are many solutions to that. So then, of course, but that's a choice of exactly solving the first order condition and making the selection when I'm making next. Okay? Now I moved, once I'm here in the plateau, if I don't know exactly what I had said, I don't keep record of that, which corresponds to keeping record of this lambda, I can easily build up examples that the whole thing will not be satisfied. Even the examples with things are not even feasible. So that's where this paper started backwards, okay? So thinking about solving this problem, because at the beginning we were assuming that we need uniqueness. We don't need uniqueness, we just need a condition like that, okay? But I think the neat thing was that then to realize that the whole thing was about, so we have these two approaches, no? The recursive contract and the promise-keeping approach. But when you do it this way, you realize that the promise-keeping is not only annoying the way to make it computing stuff. Promise-keeping is just the Euler equation. Okay? And here the Euler equation, you get it when you solve it, as we do all the time. We don't use the Euler equation as a constraint in our problems. Okay? But there was a case that we might have a little problem, which was this one. Okay? I said, okay, no, but let's keep track of that. Well, how we keep track of that? By extending a little more the co-state, if necessary. If you start randomly, almost surely you are fine because it's going to be differentiable. But since this is you're following a path and that's endogenous, if it's endogenous and you have going up the hill, at one point is a point of non-differentiability in this hill. So you will hit the point. So even if it's almost surely differentiable, doesn't mean they will for sure will be non-differentiable along this path. Okay? So then you need to know how to deal with that. That's it. So we recover the whole thing. Okay? That's it.